Okay, so for 6.2 part 2, we're dividing radicals, and you use the same rule pretty much as the multiplying. When you have radicals being, or a quotient inside of a radical, you can split it into the two radicals where the numerator the numerator is under the radical and the denominator. But it can go both ways, okay? So if you have one radical dividing by another radical, as long as the indexes are the same, you can put that under one radical with that same index. So for example, this first one, the square root of 18x to the fifth divided by the square root of 2x to the third, I can put that as the square root of 18x to the fifth divided by 2x to the third. And now I'm able to simplify this fraction. 18 divided by 2 is 9. And x to the fifth divided by x to the third becomes x squared. 5 minus 3 is 2. And that's where we're using those rules. So then I can take the square root of 9x squared, and that's going to become 3x. So here I have the same thing, except it's a cube root. But because they're both cube roots, I'm able to do the same thing. And I can put it under one radical, 162 y to the fifth divided by 3y squared. And now I can simplify that fraction first and then take the cube root of it. So that's going to end up being the cube root of, this becomes 54y to the third. 5 minus 2 is 3. So then to simplify this, well, 54 isn't a perfect cube. So I'd have to simplify that using the factor tree or birthday cake. I'm going to use the birthday cake. And if I divide that by 2, I get 27. Divide by 3, I get 9. 3 and 3, 3 and 1. But remember, because it's a cube root, I'm looking for 3 of the same kind. So what that means is the 3 comes out because I have 3 3's, and the 2 is going to stay on the inside of the radical. But I also have this y here, and 3 goes into 3 once, so that's 1 y comes out. No y's are left on the inside. So then I'm left with the cube root of 2. So I get 3y times the cube root of 2. And that's my answer for that one. Okay, so this next example is going to have ones where you need to rationalize the denominator. And we've talked about this a little bit. I'm going to go over here and do a quick example of what I mean by that. Whenever you have an answer and it's left with a radical in the denominator, you can't leave it that way. You can't leave a radical in the denominator, so you have to rationalize it, which means you have to make this, in this case, it's a square root, so you'd have to make it a perfect square so that there is no more, so that when it simplifies, there is no more radical. So with a square root, what I can do is multiply by itself. And that would make it, that would make it square root of 2 over the square root of 4. Now, when I multiply it by itself, I also need to multiply numerator and denominator by that square root of 2. And that's going to make it a perfect square. Notice that this is a square root. My index is 2. And when I multiply these, I'm going to have 2 times 2. And there's going to be 2 of the same number. It's just like if I'm doing the factor tree or the birthday cake, I would need as many as the index is to make that a perfect root. And that's what I'm looking for. And then that can simplify. This would be able to simplify into the square root of 2 over just 2, because the square root of 4 is 2. So for this one, I have the cube root of 5x squared over 4y squared z. Now, if I look to simplify anything, I can't divide the 5 and the 4, reduce them. There's no more x's, there's only one y and only one z. So I can't combine anything or reduce anything or simplify that fraction. So what I'm going to use is that same rule, except I'm going to go the other way. And this is going to be the cube root of 5x squared over the cube root of 4y squared z. But I cannot leave that cube root of 4y squared z in the denominator because it's a cube root. I have to get rid of the cube, the radical. And so what I want you to do is look at the 4 and use the prime factorization, the birthday cake, the factor tree. That's what we're doing when we do that. And when I factor that, I have 2 times 2. If it was square root, that would be fine, but because it's cube root, I would need 3 of them. So what that means is I need one more 2. So I need to multiply that with another 2, and then I'm going to have 3 of them there. Okay? So that's going to be the first thing that I'm going to be multiplying by, is that 2, to make that a perfect cube. I have y times y. Well, to make that y come out, I need that to be y to the 3rd, right? So the 3 goes into 3 once, and I would bring 1y out. So I need to multiply by one more y to make that a perfect cube. And the z is just z. But I need to make that's the cube root of z right now. But I need that to become the cube root of z cubed, because then one z is going to come out of the radical. There's not going to be any left on the inside. So to make that z to the cubed, I need to multiply by z squared. Okay, and then that would make 3 z's. So I have z squared there. And remember, whatever I multiply to the denominator, I also need to multiply the same thing to the numerator, 2y z squared. So what that becomes, I get the cube root, 5 times 2 is 10, x squared y z squared over the cube root of 8 y cubed z cubed. And now to simplify that, the numerator does not simplify at all. That stays the same. That stays cube root of 10x squared y z squared. And then the denominator, the cube root of 8 becomes 2. The cube root of y cubed is y. The cube root of z cubed is z. And that is my simplified form. If you don't understand this part of it, it's okay. I'll go over a little bit more tomorrow in class, and you can ask me specific questions in class on some of these. But try these tries on your own, and come to class with some kind of practice with it, so that you know what you need to work on. Okay, so here are the U-try problems. Give it a shot, and we'll talk about it in class. Okay. Why did the chicken cross the amusement park? To get to the other ride. That was bad. I got to get better. I will.